Hello, welcome back to the stream. I'm Jun Chan and my microphone's a little bit far. And yeah, today we are continuing with Comonads as we have been for, wow, 16 sessions. That's quite a bit. So, but yeah, I think Comonad have still a lot of mystery to unravel for me. And I still have this intuition that they are underused somehow in programming. So I feel like, yeah, who knows? Maybe this is an unexplored land with unexpected riches that we can use to our advantage. So that being the grand scheme of things, we, as per usual, bounce and whirl and follow rabbit holes. And the rabbit hole we're in currently is in a repo called Comonad Playground. And it's right now we've been using we've been looking at recursion schemes from Comonads, which is this blog post here, and also something that leads to the recursion schemes library in Haskell. And the PureScript equivalent design with the same principle with the small changes is called Matryoshka. And we have been trying to make that work for us so that we can maybe use it. The idea being that picking a base comonad will define the type of recursion that you do. And I think that to me, that means that in some sense, the comonad is giving you a context of time, because if you pick identity, then you're just sort of carrying, basically your recursion becomes something with which you carry only one single value, which is like a fault. So you just remember one step before in the past somehow. And I think that that's the combination of the identity comonad and the fixed point of the recursion itself. But then if you pick a different things like a tuple, for instance, then you're carrying the whole structure with you at each step, or you have the possibility to carry the whole structure with you at each step. And that's, I think, a paramorphism. And then with an isomorphism, you can actually give more structure to what you're carrying forward. And in an isomorphism, it's specifically basically the for instance, the substructure you were traversing. So you don't have access just to a top level structure. You can also define some kind of substructure and carry it forward. And in some sense, remember buckets to assign things to, which I suppose is the histomorphism, and maybe a little bit like a histogram if you squint. So I want to get a bit more familiar with that, make the intuition about how the comonad plays with the fixed point a little bit more concrete for me. And specifically, what we ran into last time is that we were trying to implement some of the examples that we found in this example in the blog post here, the ledger comonad. And we ran into something that we saw before, which is a Stack Overflow. And so we're going to dig a little bit deeper again into how to make laziness in PureScript something that works correctly for us. So let's just check that things are set up properly and that we get the same error. We do. So here, the error we have is with mkcofree. And so I think that makes sense, because we should really use deferCoFree. So mkcofree, I think, is strict. And so therefore, I suppose only works with finite comonads, of which I don't think there are many, in fact. But deferCoFree should give us what we want. So let's just double check that we have the signature, and yeah, that's going to create a cofree for us, and it's going to be lazily created, which is what we want. So let's get to it. The main problem, I think, is right here, is that we used mkcofree here to create our cofree, and what we want instead is take a unit and return a tuple of n, and I suppose the rest. This might work. And if it does, then I should actually be able to copy this and with proper copy paste. Let's see, how's that? Yeah, seems like maybe it will work. Well, so it builds. So there's 2 places where laziness matters. One is in the construction of code-free, and the other will be in the interpretation of code-free. And here, I think we have a problem. But I need to check because there's data lazy and control lazy, and these two things are sometimes a little bit confusing. So we import both, and here it's in data lazy that we have a problem, but it is unrolling a differ code-free. So let's just check that 9102 in the JS. Why don't we have stacks? Source map. No. Source maps. Still not. It would help. Okay, Spago source maps not working. Creating source maps. Apparently, Spago bundle app. Get source map for my project. Okay. Source output and use something like parcel. Now you can see breakpoint in action. Okay. Seems better. Yeah, we have dot maps. That's going to be better. Not sure why the -x didn't work though, but and we don't have an npm package.json here. I wonder if we can put this into a global variable, but yeah, no, it's not working. Not working. To pass to a node. Spago run source maps. And PM init. Source path. Maps. No. Dash source pop build source map to use source map. Make sure to build with source maps. Add debug configuration to the VS Code. And set breakpoints. PWA node. Replace blah.main with a compile.js file to be debugged. Not sure I like that so much. I wonder what Spago run really does, by the way. Spago.dal source maps. Dash source map. Not very obvious. Okay. Is there more in this tweet? Doesn't seem to be. So it's really parcel and so on that will give us that. Node and source maps. Okay. I suppose we can try that. Node output main XJS. I think we need to do require import that as a module, which is what we were seeing in some of the other advice. Doing this. Okay. I think, yeah, but still no source maps. let's go take a look into the outputs. Main. There is a map. There's a .map file. And yet, oh, main.pers, but look at this, it is there. Was it there and I didn't see? No, so this has the map. Good, good. Okay, so let's look at the map now, and let's learn something from it. So the actual call stack size exceeded is in main.pers 369. Which is in defer co-free right here in the Go. So it sounds like I need to defer this. Although, yeah, let's take a look at defer co-free again. Let's see, is there an example with defer co-free somewhere? Doubt it, and indeed there isn't. Okay, defer co-free. Basic co-free constructor. And let's see if it's used elsewhere. In pure script code. No, so let's look in all GitHub. In pure script. Okay, jar machine, defer co-free, blah. Interesting. Mike Sol, I have seen in the Discord being very smart. Web radiographs as streams. And you're telling me that the drum thing is actually, that's in where? An example drum machine. A co-free identity string. Oh yeah, it's several. Yes. Well, hold on. Is it? Yeah. So I'm not sure where. So my WA is my co-free, and so go of something should return a co-free, and I get the feeling that this should work. Why is this not working? Let's look at the stack again. This is called by 370, which is the line in otherwise. And this is called by data lazy, and it's called by tail and main 347, and by unwrap co-free here. And fold and tuple. We don't have more stack here. So let's look at the shape of this again. You're doing head, you're doing unwrap tail in a ref. Oh, using halogen, yeah. And you do pass differ free blah into before calling your recursive. Well, no, here like you're calling the recursive directly because there's differ free here, which makes sense. But maybe we put it here. Okay, let's do this again. Oh, right. But in that case, okay, let's try. Should type check, right? Doesn't. Infinite type. Strange. I would think that this is the same, but maybe the type checker has a problem. Maybe I can't use apply. Sometimes it seems that it's changed like that. No, that's not the problem. Okay. This type checks, but it's Stack Overflows. Okay, there's an article about laziness in PureScript in the functorial.com, or maybe here. I think maybe this is the one we want. PureScript lazy, defer and force. That's one of the things that happen underneath the hood if you use difficult free, right? Let's go to the definition. Ah, right. Oh, but yeah, it's forced when we use the tail. Look at this, mkco3 actually does use differ. So what's the deal then? I note that it doesn't use differ-free though. Strangely enough. ACD creates. I mean, given what we saw here, yeah, using the nested tuple notation, which I like as well. Okay, let's imagine that maybe. Oh, what am I doing? That maybe we need it here as well, because this is co-free too. It feels very strange. And if we force, we only force one layer, right? And then we need to take second, I think. Yeah, no, I think I'm well, let's try with difficult free inside the Go or inside the tuple. So in that case, but then we can't return that tuple. Oh, right. So we need to return a tuple and not a Go and FS1. That's the problem. So it doesn't make sense. It just simply doesn't make sense to do that. So could it be then? Let's try and interpret some ledger with something different than our crazy recursion scheme here. Let's try to use some good old Comonad or co-free thingies like, well, either explore or, I mean, actually we probably need to use explore, or we could use head a few times and just see whether actually we're actually able to make sense of this a little bit. So what's in head? Ledger label with type co-free. Oh, because this is head of co-free, right? So you're saying some ledger is ledger label blah. It's not the co-free, right? The co-free is instead the WA. So we'd want to run ledger and just hope it works. No, because run ledger is the whole thing that's meant for a GAlgebra. You know what? That would work actually, I think. But it's probably part of what's broken here. But let's try. I think this would get us a. This should give us an int, but I'm not sure it will work. I mean, it might compile. Right. No, it won't because it's. I take some maybe int. So maybe we can make it work. Like just 1, for instance. Does that work? Well, appearance, and it does give us a number. It gives us 4, which is that. How does it do that? It iterates from 0 to 5. So if I say 9 here, it needs to rebuild. Spago build. With the source maps. So that's not what I expect. So it's not the recursion of this that gives us 4. What is it then? I'm a little bit lost. So we're passing. Oh yes, no, it is 1 plus the length of the environment, which we set in some ledger at env, which is 3. So let's look at this again quickly. Right, sum ledger, the label is set at 3, and our interpreter takes the length of the amp, which is 3, and then adds 1 to the for each layer. And right now we only have 1 layer. If we do this with tuple just 1 sum ledger, and we're running this into just a maybe int. But the idea, if we run this recursively, is that somehow we transform the maybe int here as a recursion scheme. And that's a bit crazy. But I think that's the reason why we have this recursive instance here, which unwraps co-free. So when we pass gkata this ledger, when we pass run ledger to gkata this ledger, then we transform into this FA here. Oof, it's complicated. So I think this is going to be our run ledger. And if that's our run ledger, then gkata takes this ledger, takes our algebra, and knows how to swap the W from the F, and then given a T, which we want to be this ledger, we get an A. Given that we know how to operate on one F, then we can interpret a T that recurses according to F. So the idea is this guy unwrap co-free. Unwrap co-free is not in the list here. Yeah, unwrap co-free is from Comonadic co-free ledger and recursive. And the implementation of unwrap co-free in the class for co-free itself is what? It's tail. and tel uses force. So I'm still missing the idea of how do we make I mean, I suppose I think that some ledger is properly recursive according to how I've defined it here. And it should be properly lazy. To be honest, I don't understand why this would be more lazy than the MK Cofree version, but we did get a Stack Overflow at construction when we didn't use differ Cofree. So I suppose that I don't understand quite exactly why, and maybe I should try to understand that before I move forward. So why does MK-Cofree when I had the MK-Cofree here, and I suppose you're trying to evaluate the right hand side strictly because it's passed as a parameter, so you have it as a, even though one wrapper does defer it, you're trying to pass it here. So I don't know, I don't understand that. Let's look again at laziness in building blocks. So when we do defer blah, tel uses force to transform the underlying lazy. That's inside the Cofree construction right here. Let's blame. Was MK Cofree always deferred? It wasn't. At the lazy instance, at build Cofree, which unfolds the label and subtree together. With Cofree since it's strict. A specialized implementation of the lazy instance. Right, just as if lazy was a class and then you'd have a defer in the environment or something. But but this also made mkcofree defer, not just with the label. Huh. All right, the label being moved underneath. I see. So that it too can be lazily calculated, which is why we have this tuple underneath here. So is there a way that I could run this multiple times? I think I need to rebuild with this again. And it'll blow up. And maybe we can add some output in the generated code to sneakily try and understand what's happening. So that would be in main. And we log show that whole thing with lots of instances being passed, and some ledger is this crazy thing. We can build the source maps, I suppose, and then try and run with node. Okay. Aha. Yeah, of course. I don't stop after. Oh, so it was correct. Huh. Well, I mean, ideally, we're able to launch our effects a bit like I did here. So we don't wait for the result. I suppose that's maybe where we use gkata m, actually. So let's try that. So this is infinite. This therefore stack overflows. Okay, so let's try gkata m instead, which is going to be Matryoshka, and let's just double check. So gkata m. Okay, I need source code, I think, to understand this properly. Instead of taking it returns in MA, which is what we want, and so we need to pass it a GAlgebra. Yeah. So, and what we're going to do therefore is gkata m this ledger run ledger m, and run ledger m will be a GAlgebra m which takes a M somewhere in the middle, I think here, yeah, and that's going to be effect, and we're just going to, I suppose, log show that thing, and we need to call it run ledger M, and we need to import our things. No. Okay, I see. Matryoshka, where are you? You are here. And therefore we'll also import algebra M. Okay. And gkata M as well. Okay, this time you can import it. Good. And could not match type. Okay. Unit with int. Right, yes, good point. Very good point. It's now returning in unit, and that's totally fine. It is not. It's not totally fine. Okay, that's fine. We'll do a let's close let x equals blah in do log show x and pure x. And here we are returning something we ignore. And maybe log show done. Okay. Aha. GKTM requires F to be traversable. Interesting. Okay. Makes sense, I think. So let's try to implement traversable for ledger. Sounds like we should be able to infer it, but traversable ledger. Is this where we need traverse and sequence? Or no, maybe we have defaults. Yes, we have defaults. So what do we want? Probably sequence. Let's try that. Let's look at the blog post, see whether there were traversable instances created in the end for this. No. Okay. So this feels like that's actually exactly distributive, isn't it? No, but we know distributive and traversable actually sort of are supposed to have a different semantic. But for something that can be traversed like this lazily, it should just be, it kind of just should be unwrap, co-free, shouldn't it? Maybe not. Not a class traversable. I see. Actually, isn't it? No, it's not. Okay. Okay, that's better. And then you need traverse, which is sequence default. No, traverse default. And we can remove that, and then we'll have our error. So we want to be able to exchange it with basically any M that's inside. We want to be able to pull it outside. And yes, that makes sense. Yeah, and it's basically kind of a distributive law, but for a wrapping monad, as opposed to the wrapping functor that dist law are for. So is there a dist law for monads? No. No, it's not meant to be that. So if we have a functor full of MAs, a ledger full of MAs, then how do we sequence the effects? I need to look at the traversable instance for co-free, I suppose. Oh, but there isn't one. There isn't one, and but there is one. Co-free traversable functors. Co-free traversable. Oof, that's a yeah, I mean, we could try and pattern match. That would be a thing. So ledger really is, if we do a get ledger, or we just pattern match. Then we need to pattern match on the empty. Didn't we pattern match elsewhere? We did here, right? Yeah. So let's try that. Pattern match here. And we know we have an MA here. And so really we run MA and we but then that's where things will get maybe we can even do that. I don't know. Trying to get the M outside. So when we run this into traverse, knowing that I may, yeah, I think that's probably valid. We just rebuild a tuple with the label. Well, actually, we can just put the env directly in there. And then we apply that. I don't think we can do this. The good old anonymous function I don't think works in this case, but can try. And then we apply this to, well, we're doing traverse in the end. Traverse f blah applied to traverse f ma. In theory that might work, but I think there'll be laziness problems again. Yeah, anonymous function doesn't work for this, unfortunately. But the lambda might, and a no value is yes x, and traverse we need to import. There's a traverse in new type for some reason, and we need a type class for something apparently. For traverse depends on foldable. Yes. I forgot about that. And this is Haskell. The beauty of deriving foldable. Wouldn't that be nice? Okay, foldable. Where are you? Foldable. So I think we can do fold map and have the other two for free. Is that right? Yeah. So let's try fold map. Given f and an fa, f being the thing that we're interested in, so therefore this indeed we return an m. And how do we do that? This is full of a's. Given that we have a way to convert, so we apply the f underneath the, we want a monoid, so we kind of need to get at the a, so we just run fa. I don't know whether that's it or not. Fold L equals fold L default, and fold R is fold R default. that as well. Looks like it might compile. No. Folder default. Yes, I think it should compile. Okay, and we need to fix the names. And we have some type problem here. Okay. We have function from A to M. Oh, but this is a co-free here. Or is it? No, it's yes, it is. Yes, indeed it is. So I think we do what? Maybe we had A and we monoid. Well, we F had A and we also fold map F onto the tail of A. And we need to import fold map. Oh, mapend, not monoid or apply, or not apply. And right, so we might need to apply under this. Oh, maybe it's not tail A, maybe it's just, no, it's not just A. Hold on. Okay, I'll take a little break here. Okay, so what are we trying to do? We're trying to fold map. So the head of A is going to be, I suppose, what's inside our ledger. Yes. So head of A is going to be an A. The tail of A should be where we want. I'm pretty sure. What's going on? Though we did have to do this trick. Basically rebuilding underneath the traverse, and maybe we need to do the same thing here. Or here. With okay, yeah, I am missing things here, but tail A. Okay, let's do good old type hole. Yeah, of course, whatever this is, it needs to be foldable. But my expectation is that it's another ledger. I think that's where we need. No, it's the reverse. So it is tail. So what? Maybe it's just A. I remember having this error and not understanding what that meant. think it had really nothing to do with this error message. The value is undefined here, so this reference not allowed. Cycle and declaration. Yeah. Okay. Is it that it's expansion instead of F? All right. Okay. So let's try to do that here, and maybe also here. Doesn't work. That's a little bit tricky. There we go. Yeah, that's what we have. That is indeed exactly our problem, but UX equal to, oh. be just the expansion of these guys. I think I saw the co-free traversable. That was interesting. Oh, well, that's King of the Homeless. And maybe it's going to help to see some comments there. No. Co-freeness. Oof. Traversable functor CFTF. Using a final encoding. Right, it's a different encoding for co-free, so it goes a bit further than what I understand. But let's go back to co-free here. There is a foldable instance for co-free. And a traversable instance. Oh, well, in that case, I suppose I can fold map FA, can't I? And let's see. So same cycle. Should be foldable. F B A B A. Oh wow, that's really not great. That's really not great. But okay, it is what it is. Does it work if we only apply F? Seems like it does. Okay. All right, so what am I doing here? I'm supposed to have a traversable instance now. Oh, that should allow me to then run gkata m, which should be able to log show without, by just filling my screen with stands. But it doesn't work. It also exceed the stack, but this time in the functor instance for ledger. Interesting. Which we derived. By the way, if co-free is traversable, then we should just be able to do the same thing here, which is to actually traverse FMA. And I don't think we need to. Oh no, in that case we do need to rebuild it. Yeah, and we use the traversable instance in co-free. Yeah, so that's fine. Okay, let's go back to the laziness in pure scripting. I'm not sure that's the one that I remember. I thought there was a better. I think there is a Phil Freeman post for that, but it just doesn't come up. Lazy, strict. Stack state reversals. Building up thunks, won't work with other functors. So I fold over a data type into a step-by-step calculation. This is going to be too complicated for me, I think, but I wonder whether it's the same thing I was saying the other time about ZP, about zipping things in a more generic way. I don't know, but stack, I think it's something about stack, but not sure that's it either. Okay, pure script, lazy stack overflow. Strictness surprises. Lazy lists. I thought there was a better post. Did I dream that? List lazy. Maybe if I take a look at lazy lists, a lazy linked list. It's lazy list lazy, but it has a step in it. Which is actually the constructors. Okay, why? Because you want an instance on it, I think, probably. And not empty list as a Comonadic instance, and affordable and traversable. Let's take a look at those. I mean, I suppose we can look at just the foldable and traversable for regular lists, and it defines use this fold L. Go is needed to ensure the function is tail call optimized. Maybe that's the problem. That with fold map, it won't work with fold map. We need to pick fold L and then define fold R and fold map in terms of it, because we need to have some direction, bias towards some direction. It is tricky. It seems like what repeats here is the Matryoshka fold and the bind, which makes sense, but so then maybe we need to defer. This apply here. But this is the traverse of Kufri again, right? So, I mean, I'm assuming the traverse of Kufri, traversable instance and foldable instances are written in a way that makes them smart, right? Foldable, blah blah, head, folder, go. Right, I suppose this go is the thing for tail recursiveness again. Maybe we don't. Maybe we don't derive the functor instance actually. Yeah. Maybe we say map f l equals same thing basically. We need to take this guy and we need to apply f underneath it all, I believe. Map fa. That's what I would think it is. Using the functor instance of Kufri f, but apparently not. Why not? Oh, yeah, right. You'd want to, we need to rebuild the thing similar to this, which, by the way, I bet wasn't the problem. Oh, no, this was actually a problem, yes. So we do this. No. Okay. Oh, yeah, of course. I think we can just say this with actually map f a. Is not. Yeah. Okay, maybe we won't blow up the stacking functor now. We, in fact, don't seem to be blowing up the stacking functor anymore. We are blowing it up elsewhere, which I assume maybe is progress. Can we spot repetition here? Weirdly enough, it's in. Let's do the -x and the whole source map thingy again. Differ core free. Go free purse, bind purse, and go free purse. Tell. Blows up into a slightly different spot. What's here? Index 596. Comonadic free ledger. Can we have more stack trace? Yes, I don't know how to search in here. Stack. Show stack traces on process warning. Stack trace and use IO trace, private exit. And that's pretty much it. Okay, longer stacks in node traces. I see. Infinity is a little bit crazy. Ah, there we go. We can stack trace limit. Default 10. Okay. Let's do 20. And fold, Matryoshka fold is one of the potential culprits here. So that kind of makes sense. Let's see, does it make sense? Fold will be called by Jikata M, I believe. What do you mean, no definition found? What's going on with you? Okay, why don't you go to Jikata? You can't find the definitions. Okay, let's save. Maybe the build has gone a bit. Maybe because of the -x or whatever. Okay, let's rebuild. Build. Okay. Can't find definitions anymore. Not the best, not the best. This is not on one of my 014 projects, it's not. So let's sure, save, and then let's reload. Let's see what's up. There we go. And that is indeed in fold. And so when you do the loop here and bind and the things, to use map, I think I should try on a co-free, like not something, not ledger. I should try, but I think I'm going to leave it here, but that's what I'm going to do next time. Unfortunately, we didn't get very far, but we haven't fixed this. Therefore, we need to create a simpler example with co-free with some infinite co-free and g kata m. I suppose I could try to do a little bit of that now. What would it look like? Okay. Well, it could be a co-free of, in fact, maybe int and int. And we could make it feel a bit like this guy. Right, where we say a tuple of maybe int and blah. And yeah, we can pretty much say, here you go. You're the same thing. And then we have all the instances in theory, the default ones. So let's try them. And let's try with, oh yeah, well, we need to run something. Gkata m. And we're not going to need a, actually kata m might be sufficient. Am I right? Matryoshka. So those are the dists. And there we go, kata m. Yeah, kata m should be a simpler way to get where we want, which is good. And we don't need a distribution law, I don't think. And our algebra will be run simpler, and we'll put simpler, and we'll pass simpler there. And we just need a run simpler, and run simpler is going to be a algebra m of our monad effect, our functor, I think tuple may be it. Is that right? Yeah, I think so. And int. And then we'll say run run simpler. We'll take we'll give a now, and we'll just extract the L. This might work. Boom. We might need this to be in log, right? Kata M. I want to log things. Yes, we want to log things. So let's log them, and then we need to return. We need to do a little dance. Hoping that that's not the thing that's actually killing us. And what's that? Empty int with type tuple. Why would you need an empty? Oh, because cofree requires so that's the recursive class, I think. Here or the co-recursive one. Which one is it? It's the recursive one. Yes, class recursive. Say that if you have a cofree, you need an empty. Somewhere. And I think yeah, I remember trying to understand that, so maybe we'll, as a byproduct, we'll understand that. So it's trying to solve this type constraint. So when we do kata m run simpler, kata m again, we're expecting to have a recursive tf, and f is this. Tuple maybe int, and our t. Right. Right. So hold on. Empty int with tuple. Are you seeing this? That sounds wrong. But that's obviously important, because when I had to write a recursive ledger instance, and I just used unwrap cofree, but basically using, I think, that model. But I think I was also inspired by what's in the Haskell library. But I still don't understand what that means. I mean, hold on. In this case, we're saying that mu f is a loop of f's. So we're saying that a co-free FA really is a loop of FTAF. So if that's the case, then co-free FA, okay, hold on. If that's co-free FA, then we're saying FTA F. I mean, then obviously we need to change that stuff, but that compiles. And does it run? Also blows up the stack. But here, I mean, it's a little bit strange now, because now, I mean, FT is the environment Comonad transformer. I don't know that extracting is the right thing to do. Can I pattern match? What can I do with FT? Yeah, I should be able to pattern match. So let's pattern match FT. Let's off tuple, and let's ignore that. And here we have an A, but it's wrapped in the W. That's what? That's not even, that doesn't even make any sense. Are we talking about the same FT here? Control Comonad F trans 2018. FTE. FTA. How does this work in a monad, in a M context? I'm now having a few thoughts. One is, can I try with a pure algebra, not in the monad? And then can I build like a take for co-free, so that I actually build the co-free lazily, but don't have it in the monad. I mean, underneath the hood, it's in the lazy, but that doesn't leak, I don't think, and then use a take so that we actually yeah, I mean it would be good, but it's not the whole story, right? Because we do want to stream, ideally. We do want to be to see things be productive, meaning able to log in a way that works with the node async IO model. And then the other thought that came to me was the fact that this whole like co-free as an infinite structure made me think about actually saying, well, like the Dunai construction, where you, by adding a transformer monad and making that, maybe you add the semantic of escape or quitting, or throwing an exception. So that's a way to terminate an infinite loop. And I suppose that that's exactly what I'm trying to do here by passing a tuple of maybe int into my simpler thingy. Yeah, so I suppose another way to look at this is to say that tuple is my f, and maybe int is my a. Does that work? I don't think it does, right? Because no, it won't, because tuple, no, it won't, of course. Tuple is not tuple is a bifunctor, it's not a functor. And this empty comonad sounds completely wrong. I mean, does this even... So empty has an int in it, and then the f, or the transformer, so that's the e. Okay, I think I misread empty. E is the environment, and it has an int in it. And the tuple maybe int is our wrapping comonad. Not the best looking comonad, but I suppose you can always extract something from it. I mean, if you want to extract an int, no, you can't actually extract always an int from it as a hold on, as a comonad. Yeah, no, you can, because tuple of maybe int and int is always going to have an int inside, I think. So here we have a WA, and so we lock show WA and we extract WA. So that should type check, and also blows up. Laziness in PureScript is hard. I wonder whether I should do a little sub-series on laziness in PureScript, so that I take this from a more principled standpoint in order to solve these problems. That's possible. I thought I understood it, but I think maybe I forgot it. To Ed's point about space repetition here. Definitely haven't been doing this properly. Laziness, laziness. I really thought there was a better article on laziness. Overflows. Lazy go-free constructor. Let's look at this because part of the conversation here was also about hoist go-free being strict. Pattern matching on go-free. Tail used to force T, and that's it. Now it forces the tuple, which is fine. This stuff looks tail recursive. Head and tail. What if I don't duplicate that value here? So it goes up, but differently, right? Hard to tell. Yeah, I mean, there's something here. then in that case, it would be about kata's implementation. And I mean, it's possible that this stuff doesn't work for lazy data structures. Very possible. Stack usage. Oh, there we go. Medic fall with trampoline. Hilo M, Get M. And the other is clones and joker paper. And I suppose that is what we're doing. We're doing function composition. So is that the joker? Because then I see that, oh, what? A new type over normal function. It guarantees stack safety. That's pretty cool. But we don't know which function composition is actually causing our issue, do we? It might be inside kata, but let's look at the let's look a little bit closer at Masaidu's Assad's example here. The regular kata morphism and list specific iterative kata refers to stack in an array. Be specific and we'll work with another base functor, which is kind of what we're trying to do here, I suppose. Ah, the Scala version of Matryoshka, huh? And a recursion scheme talk. So yeah, I mean the clones joker paper, that's exactly what we were seeing in stack safe traversal via dissection. Turn a fold over data type into a step-by-step calculation backed by an explicit stack of intermediate compilation. So as long as I suppose our co-free is dissectable. It could be also that we just need to use a tail recursive monadic value actually. Yeah, hold on. How's that work already? Stack safe monadic tail recursion. Which I mean, we're not exactly using monadic recursion here explicitly. It's actually in kata that that's the case, but Terek function, control monad rec, A to step AB, which sounds a lot like what list does. Transit several monad transformer from the JavaScript transformer that we're using the following type class. Monad rec, where telrec m, blah. Is that this section? Left, right. Oof. It's not easy to understand. Steps by functor is a loop containing the update segment. Draw down containing the final result of compilation. But the thing is, I can't use telrec here because my loop is in gkata m, isn't it? So I need to implement another kata m where I use telrec. Isn't that the case? Gkata m rec, right? Well, let's try that. Or kata m rec for a start. How about that? Where we need a monad rec. And then we tell rec m. Not right. And project coming from recursive, okay. Okay. Don't know what's happening. Matryoshka, it's let's hope it's exported. Where did the Matryoshka bits go? Right there. And we said it's just project. And then you need some step stuff, which makes sense. And so the step stuff works by returning right. We don't know that will ever be done because of the recursive thingy here. So we have to push telrec m inside somehow, don't we? How do we do that? F being the algebra. project giving us only one step. Go here being of type blah to step. No, not like that. Okay, I think I need to see a fold using this thing. How does it work? Some examples maybe. Loop. Okay, maybe I need to say pure script tailrec fold. Tailrec package. Tail recursion optimization for recursion. Prefer fold to explicit recursion. Yeah, indeed. How do we do fold with tailrec? Stack traversals and dissection. Run. Not what we want. Monad rec. Monad rec is exactly what I'm looking at. Recursive monads elsewhere. Skitter. Try to do a treefold. Okay. Trying to do a treefold like this. Da-da-da. Don't know how to use tailrec inside this. It happens inside this concatenation. Really messy. MD trippiness with primes and variable names. Oh, right. Does your function have to be tail recursive? Your tail link isn't. Tail link. Where is tail link? Doesn't help. But let's go back to the search. This uses tailrec. Using monad rec, we can get a safe traversal for any dissectable container and any monad rec simply by switching from a regular tail recursion with tail rec to a monadic tail recursion with tail rec M. Step. That sounds pretty interesting. Can we do this for co-free? And is there a module for this? Or some code? No pure script in the list. Ah, pure script safely. Different repo. Pure script safely. Okay, well, let's try and find it. them. Ready control period stack safe. Replicate them in stack safe. Control stack overflow by large input. Boom. Make it stack safely combinator. From the wrapping and unwrapping for us. Okay, maybe that's simpler. But that looks old-ish. Pair-natural transformation, lift and lower actions. Would that work for us? Oh yeah, I think it might. Let's try that. Let's see if it's in the package set. It is. And then let's try it. And I think it takes a function of unit to blah. It does say left though. So what's the deal with that? Otherwise do left x and then go blah. Not super clear, and that's archived. So looks like there's some kind of safely is a monad homomorphism or something. Do we have more info here? Lift and lower. Go const xxs. Lift fx. So maybe lift f. So where won't work? Yeah, we actually need in Go. All right, it is, I think. And you're going to import it. What's going on with the ID? Please restart the ID. I think my Spago build -6 are kind of killing the script ID for some reason. Okay, I see you're not gonna help. Fine. Control that safely. Maybe need to build a module once. Yeah. Oh, that's not good. Value kits are okay, yeah. Go. So Rift. Well, maybe. That'll be the last attempt for now. So we have a bunch of things to look at a little bit more. We have safely. Actually, yeah, that's fine. We have well, we have the dissectable approach. We have just using the regular tailrec. And I suppose we have stack safe function as well. We could give it a shot if we know where composition is causing us trouble. But the overloading of functions sounds pretty radical. We could do a melodic fold with the trampoline as well. Whatever that means. I mean, I've heard about trampolines in order specifically to solve some of these stack issues, but apparently it will require using a high-low M rather than just kata M. Not sure why. What's a high-low in Matryoshka? Show me. There's no high-low in Matryoshka. Okay, so show me recursion schemes. And now that's for refold. Ah. All right, that'll be it for now.